Let us move on. Okay, so the next, yeah.
Data files get fixed.
The data files have been fixed. I apologize we had the wrong files in there. Joe and I miscommunicated, but now he's put in the new ones. So the files you need will be in the data files session, in the repository. Okay, so this describes what we just did, right? To play with estimating and looking at coefficient estimates, coefficient significance, model fit, etc. And now I want to move to a different section in which we're gonna actually teach you how to load in real data, how to specify a hypothesis, how to test the hypothesis, and how to actually start the process of what real science might look like. Okay, so I'm going to develop a couple of cases, and the data is available in the data repository, so you should have that on your sheets. And the first case I'm going to cover is called Charitable Giving. I don't have you sign a non-disclosure, but you know this is somebody else's data, so by fair use in a class, I'm giving you access to this, but you cannot publish anything about this data set without the permission of the authors of this paper. Everybody good with that? Okay. So don't distribute this, just use it here. So the idea of this study was to figure out in a social psychology sort of format, what are the things that influence causally how much people give to charity, right? And the experiment was essentially done with about 100 people in which the people were actually given some money, and they were allowed at the end of the experiment to decide how much of that money, if any, to donate to charity, and they could voluntarily give any of their own money to add to that sum, so that the amount they gave to the charity could be anything from 0 to whatever they want. It was an experiment, so there was a condition called the tangibility condition, and in that condition, the groups were randomized into a group in which the description of the situation, was quite concrete and vivid, and so the level of imaginability was either low in one condition or high in the other, at least by intent, right? And we measured how much people had sympathy for the target of the donation, and we measured how much impact they thought their donation might have on the target of the donation. So you can imagine situations in which you felt very sympathetic, with who you were giving money to, but you just thought that whatever you were going to give, it would have very little impact anyway. Or you might have very high impact, but you don't have much sympathy for the people, or you had both, or you had neither, right? So the real question at hand was, when you change these descriptions of the charity target, would you change how much sympathy people felt? Would you change how much impact they thought they would have? And which of those mechanisms, sympathy or impact, would have a bigger effect, on the amount they donated? So that was the basic question. So these were the variables, that were actually underway and studied. And the first thing that was on the table was to have a hypothesis, theoretically, that the authors decided was a reasonable causal description of the situation, and to test whether or not that hypothesis, explained or fit the data, So this is the hypothesis, and it is the tangibility condition would affect how imaginable, the scenario and the targets were, and that would have an effect on how much impact you thought you're going to have, which in turn would impact how much you donated, and that would also have an effect separately on how much sympathy you had for the target, which would in turn have an effect on how much you donated. So this was the model, and the task was to estimate the parameters of this model, and then to see which paths were strong and which paths were weak. So now I'm going to go into Tetrad. I'm going to show you how to load in the data, and then how to actually specify a model like this and how to test it in the ways we've been testing. And then I'm going to turn it over to you to do the same thing. Okay? Okay. So starting from a blank session in Tetrad, if you want to load in data that you've collected or someone else has collected, the way to do that is to take a data box and put it on the workbench as a blank thing. And then double click it. And then there'll be these pull down menus about all kinds of different things. Data wrapper is what you want to choose. Say OK. And then you get a blank frame for the data. And then you go up to the file menu and you say File, Load Data. Then you have to identify, right, the file that has the data, right? And you can do that in comma delimited, tab delimited, white space delimited, but it should be a flat text file. So in this case, charity.txt is the file that you should now have access to in the data sets. Everybody see that there as you have it now? So while you're not now, but when I set you loose, go ahead and make sure you get charity.txt because that's going to be the file you need to upload. So from inside Tetrad, find the directory that you saved charity.txt to, and then just say open. And then what you get is on the right side a depiction of what the data looks like in the file, and then up here you get the parameters you need to set so that file loads in the way that you want. So the first thing is whether it's tabular data or covariance data. In this case, it's tabular. And I'll go to a second case where it's covariance. The delimiter is white space or tab or comma. The variable names are given in the first row, yes. Right? The case IDs, no. And then the only thing that's really interesting were sometimes if you have a data set and the number of different values that data set, right, has for a particular variable is small, like there's only 4 or 5 values, right? But you don't want the program to interpret that as a discrete variable. You want it to interpret it as a continuous variable, right? You have to set this row as integral columns, right, with a small number. Yeah, question?
As far as I know, the charity data is discrete data, but why the values look like continuous variable, continuous values?
Because it's now interpreting those as continuous. So if I take a discrete number and I interpret it as continuous, it'll put .000.
So it looks like a continuous, but the Tetrad understanding is the discrete type?
No. It's interpreting this so far as continuous variables.
Okay.
Even though the variables themselves, right, are discrete, but they're on an ordinal scale from 1 to 7. So they can be interpreted as continuous for approximate purposes.
But my question, if I know the continuous value data, then it doesn't look like the same like this. I mean, how can I distinguish the discretized data or continuous value data?
It's through this box right here, right? If I have only 5 different values that occur in the data, right, and this number is above 5, then it'll say, oh, I only have 5 values. That's discrete.
Yeah, but maybe my question is there's a 0.0000. Maybe the original data don't have 0.0000.
That does. It has 0. So let's take this offline. But I mean, this is an important question you need to know the answer to. Okay, if I say load and I get no error messages, then that's probably good. And then if I say save, now I have the data, and that's telling me that I have what I should. So I have 94 cases, and all is well. So that's my data. Now, I want to specify a hypothesis that matches that picture I showed you before, and then test that hypothesis against this data. So the first thing is, yeah?
Sorry, another question on the continuous versus discrete thing. So suppose in my data I know one variable to be discrete and it has, say, 7 known values, and I know another to be continuous, but unfortunately it's sparse and has only 5. How do I...
The way you do that is put them all in as continuous, right? And then we can discretize one variable at a time. It's a little bit, right? That'll be the way you do it? Yeah. So, I mean, I think maybe Joe and I will confirm. It might turn out that we do a session on Wednesday about discrete, continuous, mixed. So, because I think this is going to come up in a lot of people's data. Yeah.
Could you import data as a string?
Say it again.
Can you import a string?
Just loading the data.
Yes. I think put quotes around it, and I think it treats it as a string. Okay, so the first thing I do is build the graph. Now, you need to have a graph that has variables that have the same name as in the data to test that model against the data. So there's an easy way to do this and a hard way to do this. The easy way is just to drag the data set into the graph with an edge like this. It looks like you're trying to build the graph from the data directly. You're not doing that. What you're doing is you're just giving yourself the same names that are in the data as a starting point for building your model. So that's very convenient. Now, how to build the model? Well, the first thing you want to do is arrange the variables to have approximately the same spatial relations. So let's drag things like this. Now let's make the same edges like that. And now there's a handy feature that will also help you if you are anywhere inside this graph editor and you right-click. You'll get this layout button, which allows you to do all sorts of different layouts. But if you copy the layout and then go into a different window when the variables are in a spatially different place and say paste the layout, it'll pop into the same spatial relationship. So you can compare things easily. Very handy thing. Okay, so let's say save. And now I want to estimate, right, the parameters of that model from the data. So what do I do now? I got to have a parametric model. So let's do a parametric model, and let's say not a generalized SEM, but a SEM. So that forms the same graph, and it gives me parameters that'll tell me, right, the linear influence of each variable, right, from its parents, and then we'll use that to say whether or not we think, right, these different pathways are of a different strength. All right. And now I want to actually estimate the parameters of this model. So I put an estimator in there and put the data into the estimator. So now the moment of truth is here. I do the estimate. Okay. Now let's see what I find. So this coefficient has a p-value of 0.01, significant, and it says that the tangibility condition, right, did affect imaginability, right, if this model was correct at that degree. Imaginability has a positive impact on impact, p-value of 0. Has a positive impact on sympathy, p-value of 0.0006. So according to this model at least, the way they set up the experiment really did have a substantial effect on whether you thought you were going to have an impact and whether you thought you had sympathy for the targets. And now let's look at whether impact had an amount. Yes, impact seems to have 0.26, which is a p-value of 0.0079. And it has a p-value of 0.05 for sympathy, so it's marginally significant for sympathy. 0.059. 0.058, sorry. Okay, am I good to go, or what should I do now? Model fit. Oops. Right, if you can read it, it has 5 degrees of freedom, which means there's 5 degrees of constraint that are imposed by that graph. There's 5 different independent constraints. And the chi-square is 141. And the chi-square should be around 5. So the deviation in this model is 141, where the deviation should be 5. So there's way more deviation than there should be. This model you can throw out in a minute. And the sample size 94, it's pretty tolerant of deviation, right? So this is really not too good. So the RMSEA is 0.54. That should be right much, much lower. The CFI is 0.6. That should be much higher. The BIC score should be much lower, and the p-value should be much higher. So there's just nothing in these model fit statistics that's encouraging at all. So the causal conclusions we hope to draw Sorry. Okay, let me show you one or two other data sets, and then I'm going to turn it over to you guys and have you load this data in and go through this hypothesis testing. And then, it's now 3:15. We're going to walk around and help you, but that'll be it for my instruction for today. I'm just going to have you play with this data, I specify hypotheses, test them in this way. Yeah?
So now what we want to do with this data?
Great question. That is the question. So what are you going to do now with this data? And there's a couple of options. One is try to fix the model so it does fit the data, right? How would you do that? Right? There's lots of options there. You might take the edge that's the least significant and throw it away and then try to add other edges that make sense. There's lots, even though there's only 5 variables here, the number of possibilities is very large, right? But I invite you to go ahead. Take your shot. Tetrad has a better algorithm that will search from the beginning and then search for among all the models to find the ones that fit the best. And then what I'll do tomorrow is we'll go through that on this case and add background knowledge so that we're only looking for models that actually are plausible and make sense, because that's very important, right? If you let it search over models that don't make sense, what typically happens is it comes out with an output that doesn't make sense, and you're like, oh, what good is Tetrad? This doesn't make sense. Well, don't search for a model that doesn't make sense. Okay, so that's that. Now, if I go to a new session and I want to try a different data set in which I load a covariance matrix in, right? I do the same thing, put data, say OK, load data. And this time I'm going to load in that Timberlake and Williams with political exclusion and foreign investment by going to the tw.txt. And when I open that, what I see is I get a correlation matrix. And this is in a different format. And so to load that, I go into here, and it's not tabular data, it's covariance data. And I say load, save, and that's what I get. And so that's telling me that it's actually appropriately loaded in the covariance data. Okay. So I have that. Now to reproduce the regression that Timberlake and Williams did, right, without doing anything like specifying a model, there's also this box called regression. So it's handy to use because you can do regressions. Just drag data into it, and then say multiple linear regression, and then you have to pick a response variable, and you pick the input variables. So if I pick the response variable as political exclusion, and then pick the predictor as foreign investment, and say execute, what I get is the coefficient is -0.175, which is the correlation between them without correcting for other variables, p-value of 0.14, so it's not really even significant. Then if I include En and CV and say execute, now I get everybody significant, and Fi is flipped in sign from -175 to positive 0.227. Right, which is what I showed you in the prior things. Okay, so that's the way to get into covariance data. And for the final piece, it's really interesting to load in the IQ.txt, lead and IQ.txt, which looks like this. And if I say load, I get this covariance matrix. And now let me go back and explain the variables for all these things, and then I'm going to set you loose. You can just play. Have fun. Okay. So I did this, right? And I did that. And now political exclusion, the slides will tell you what the variables mean. Right? So you can go ahead and play with it. And I showed you this before too. And I did a regression, right? And you can build an alternative hypothesis, right, which is a little bit less structured, but go ahead and try it and test it against the data and see if you can find the model that fits. And then the lead and IQ case, right, came from data that Herb Needleman collected in 1979 in Boston among hundreds of school children, in which he measured how much lead was concentrated in their baby teeth, right? Because the amount of lead that's in your baby teeth is a fairly good measure of how much lead you've been exposed to cumulatively since birth, right? Blood is a very short-term measure of lead, and so if you ingest a lot of lead, right, and then you stop ingesting lead for quite a while, your blood actually eventually tapers off because you get rid of it through your kidneys. But your baby teeth actually provide a pretty good permanent record of your total accumulation. So he measured lead in the baby teeth, he did the child's IQ score, he did the parent's IQ score, he did how many mothers' years of education, how many number of live births prior to having the child, at issue, what the mother's age of birth was for the child, what the father's age of birth for the child. And these were the variables, after lots of preliminary analysis, he came up with to figure out what was actually what in causing the children's IQ. So the question at issue for this was the exposure to lead having any effect on the child's IQ? Right? And that was in 1979, that was a very important question which we did not know the answer to. Right? Now we're much more confident that we know it. Right? And what the issues are methodologically and causation here are very interesting for this case. Okay? So you can load either the lead IQ or you can load the lead and do it from the data. I'd urge you to do either one. Okay, so go ahead and load those files in and start out by building the charity model and estimating it and seeing you make sure you get the same results I did, and then have fun and specify alternative graphs and play with it, and we'll go around and just help you make sure you're good. Question?
The R squared from regression, is it adjusted?
I don't remember. I don't think so. Joe, you might remember this. Is the R squared for the regression an adjusted R squared or a raw R squared? I can't recall. But why don't we make a note, we should add both. Oh, you can see here that the R squared is 0.8. That's an enormous R squared. So there's really a lot of variation you're capturing, right, in political exclusion from these three. So that must be an unadjusted R squared. It'll go down when I adjust.
Question here.
Yeah.
Can we insert interaction terms in the regression model?
Not unless you put them in as a variable. So this is a good question. So let me show you how I think I can do that. So if I have the data and I make a copy of it, right? No, I can't do it here. I've got to have raw data. But in the other one, hold on. So if I do calculator, and I say, give me another expression, like SI, sympathy and impact interacting, and that equals sympathy times impact that'll compute that new variable. And then I can then use that as an interactive term in the expression.
And the regression here only for linear regression?
There's other ways, yes, the regression is only linear. Let me see if I have another, hold on. I can do logistic. And I should remind you that if you have any other things you want to do, you can save the data to the desktop and then run it into your own program. Yeah. Absolutely. You can just transfer, yeah, that's right.